Right, hello everyone. This is Saul Matthews at Synaptec. I'm the commercial director here, and I can see quite a few of you are already joining up, and the participation list is building here for this webinar. I'm going to give everyone, as we traditionally do, a few minutes just to settle in, because some people are, like us, back-to-back in meetings today, and we want to give you time to join up. Yeah, that's worth waiting for. It's already doubled. So just at the beginning here, while we get going, I'll give everyone a few housekeeping notes so you know what's coming. First of all, I'm sure many of you are familiar with this format now. The attendees in the audience here are muted during this presentation, so I'll do an introduction and then introduce Philip in a moment, who's going to do most of the speaking for you. If you've got questions during that conversation, because Philip's going to be throwing a lot of concepts and a lot of technical information at you, we can't obviously interrupt that flow for the benefit of everyone else, but please use the Q&A button, not the chat, the Q&A button, because we've also got a team of engineers on standby managing that channel, and we can answer those questions live if possible as you ask them, or at the end we'll try and gather up the most popular ones and ask Philip to speak to them again if anything is not clear. The idea is to make sure all of you walk away from this with a good understanding of how this works. So that said, if the questions are particularly complex and it's probably not suited for immediate response, we can always ask for you to sort of talk to us offline, and if you share your contact details, we'll be happy to follow up with you. So looking at the time and looking at the number of participants creeping up, we'll be able to make a start in a second. So this is another webinar in a series which you'll find on our website. So that's Synaptec, where you put the dot between the T and the E of Synaptec, and you'll see on our events pages all the upcoming webinars. A lot of the future ones that you'll find on our website are about specific applications. We did one recently about cable fault detection, and we're going to be doing future ones about other kinds of condition monitoring and automation enhancement schemes that we're involved with across transmission and also now offshore wind operation. But this one was a kind of comeback by popular demand. So we've asked Dr. Philip Orr, who is our managing director and the co-founder and co-inventor of this technology, to explain to people what distributed electric sensing actually is. And so literally, how do our systems work? Because some people do need a bit more understanding of the mechanics of these systems. So we're going to pass over to Philip in a minute, who's going to walk you through those slides. That'll probably take 20 to 25 minutes. Please keep the Q&A questions coming. We'll summarize them at the end. And as much as possible, we'll leave time open with the screen open and the mic open, if you will, at the end for about 5 minutes, just in case there are last Q&As prompted by some of the to and fro when we're responding. It often prompts more questions. So with all of that said, I'm going to go silent and ask Philip to take over the slides and the microphone, and we'll talk again at the end when he's finished. Thank you. Off you go, Philip.
Thanks very much, Saul, and good afternoon, everybody, or good morning, depending on where you are. As Saul said, my name is Philip Orr. I was one of the founders of Synaptec, and it's my pleasure today to speak to you a bit about the detail of how our sensor systems actually work, how the underlying technology functions. So as Saul said, throughout this, questions will occur to you. Please ask them in the Q&A, and a team of very capable engineers at Synaptec will be on hand to reply, and we'll probably address the most interesting ones again at the end. So I'm going to start by telling you a little bit about the company, then we'll get into the technology, and then we'll finish up by talking a little bit about the capabilities of that technology. What are the primary applications for it that exist today? So Synaptec is a 6-year-old company based in Scotland, and we commercialized for the first time distributed electrical sensing technology. So this fundamentally allows us to use fiber optics, which are embedded already in overhead lines, underground cables, subsea transmission cables, and so on, to use that fiber not as a telecoms medium, but as a measurement medium for electrical parameters and also for mechanical and environmental parameters. So the ability to measure electrical parameters passively and over long distances and at multiple points is completely unique and gives us a lot of new capabilities. It allows us to measure high quality, unprecedented speed and range, and also price compared to traditional systems. The company started out in transmission and distribution, and we've worked with the UK operators like Scottish Power and SSE Networks since the start of the company. We've worked with transmission operators in Europe as well to deploy a whole range of different concepts in protection, automation, and control. The company is backed by Williams, the traditional F1 team from the UK, who are experts in mechanical engineering. And we're also backed by the offshore renewable energy catapult, who are helping us to introduce this technology into the offshore renewables sectors. And we've got a very interesting project coming up soon with Vattenfall in that area. So let me try to set out a bit about the key aspects of this technology. So we deliver completely passive sensor networks, and I'll get back to that later and tell you exactly what I mean by that. And these networks allow us to very securely and very quickly deliver high quality data on the electrical and mechanical aspects of a power system back to a central location at the speed of light, and we remove the need for a lot of the traditional supporting infrastructure at each of those locations. So then we have all that data back at a central point in a very timely manner. We can then correlate and analyze that data in a way that would be very difficult if you did it with disparate types of different systems, bringing that data together and synchronizing it. Fundamentally, we go a step beyond what you can do with traditional synchrophaser schemes, in that we are sampling the continuous point and wave, and we have all of that data available for protection, power quality, dynamic rating, all at one location, and we can do all those functions. And this allows us to then build on that data to deliver insights and decision support for a whole range of electromechanical assets and power networks themselves. And that allows us to reduce the capex associated with traditional schemes and also of new schemes, and it allows us to streamline the opex by giving a greater level of granularity and awareness and decision support for power systems. The architecture of our sensor networks is generally the following. We have an active unit that we call the Interrogator, which is the only powered unit in the whole sensing system scheme. And it takes traditional DC power, it takes a time sync signal. The key aspect is that that connects to one of the fibers that go into the conductor, and then it can reach out from that point over 100 kilometers to gather in measurements of voltage, of current, of strain and vibration, or of point temperature of an asset. So we can mix and match any of those electrical and mechanical parameters. We pick them up at remote locations and bring that data back to the central point, traditionally in the substation, where we make use of it. The key thing for electrical engineers here is that the electrical sensors that we provide are IEC compliant for 0.2 metering or 5P protection. And the timeliness of the whole system operates within the timescales for IEC 61850. So what this means is that from a single platform, you can do protection functions, you can trip breakers, but you can also derive from that same data and from those same measurement locations, without duplicating anything, your power quality, your synchrophasers, and you can start to look at correlations between the electrical system and the mechanical system. Now, the way that we install these sensors is very like typical CTs and VTs, except that the installation procedure no longer involves copper secondaries. So there's none of the traditional safety requirements that you would need for having live copper secondaries and having an outage there. If we can go around an insulated cable, for example, then that is a safe installation procedure because we have no copper secondaries. Everything is connected by optical fiber. So we use standard telecoms fiber. No specialist fiber is needed. No new fiber needs to be laid. If you've got fiber in your system, you already have the infrastructure that is required to deploy our sensor networks. So we can use the fiber that's in OPGW, for example, or in subsea cables. We can deploy 50 sensors per single fiber core. It's a single-ended scheme, so it doesn't need to be connected from both ends. And we can reach out over 100 kilometers and gather in multiple measurements. And we'll talk later about what that really enables us to do. So I mentioned earlier that the sensing technique is passive. So what do I mean by passive? What I mean by that is, in the electronic sense, it is not an active circuit. There is no power supply requirements. There is no electronic processing happening at the measurement locations. So it doesn't need a power supply. It doesn't need a time sink. It needs no GPS. And because of that, everything is mechanically simple, electrically simple, and more robust. It doesn't need housed in a piece of civil work like a building in order to keep it safe from the external environment. You have an absolutely minimum amount of capex to make at each measurement location in order to get metering or protection class measurements. So that is just a fundamentally new proposition. So how do we do that? So I suppose today we want to get into a little bit more technical detail about how we do that. So Synaptec developed an optical type of sensor that utilizes a very common type of fiber optic sensor called a fiber Bragg grating. Now, a fiber Bragg grating is an optical sensor for strain and temperature fundamentally. And the way that it works is, if we send broadband light, which is light of a whole wide range of frequencies, down the optical fiber, each of our sensors, each fiber Bragg grating, reflects back a very well-defined, tightly defined wavelength of light. Now that wavelength allows us to work backwards and find out what was the input that caused that. So if we vary strain or temperature, then the reflected wavelength from our FPG will shift up and down in terms of color. So that's the fundamental platform that we use in order to get at a measurement of strain or temperature at those locations. FPGs are low-cost devices. They've been around for 30 years. They're really commonly used in structural health monitoring applications. Because they're based on wavelength, the multiplexing of them is very simple. We can put 50 of them in one fiber. Each of those have a different color of light, and so they're each transparent to one another, which means that at the interrogator in a substation we can see all 50 of them simultaneously, and the bandwidth that we've got on our measurement is limited by how fast we want to sample at that central location. So the interesting thing is, how do we then tune that to measure electrical parameters? And what we do there is we use a piezoelectric element. So as I'm sure most of you listening know, piezoelectric materials are those that expand and contract microscopically in response to an electric field within the structure. So fundamentally what our sensors are doing is they're taking a voltage or current that we want to measure, and they're converting that passively into an electric field aligned along a piezoelectric crystal. And that piezoelectric crystal is then microscopically expanding and contracting along the field line direction. And we are then measuring that expansion and contraction very, very accurately with our optical sensor. So in effect, what Synaptec's technology does is it takes a primary or a secondary electrical quantity that we want to measure, and it converts it first into a microscopic change in the dimensions of a cuboid of this piezoelectric material, and then into a change in the color of light that that device passively reflects. So that whole process is automatic, if you like. It doesn't need any external power to operate. And the speed at which we get the information on a measurement back from that point is about the same, is literally the speed of light in fiber, which actually is about the same speed as a traveling wave in a conductor. So it's about 5 microseconds per kilometer is the delay. And that's a really interesting point, because that's how at Synaptec we can timestamp our measurements remotely without having GPS there, because we know precisely how long it takes the light to travel in analog form from our sensors, which could be 50 kilometers away, back to our interrogator. If we take the piezoelectric device away, what we're left with is effectively a strain or vibration or temperature sensor. So using the same fundamental technique, whether we couple it to the piezo device or whether we couple it directly to, for example, the surface of a conductor or an asset, we can then use the same technique to deploy compatible sensors to measure voltage or current, and also temperature and strain and vibration. Now, each of these come back to the same central system. Each of them is accurately time-stamped, and we have all that data available for use, and available actually from point of measurement to publishing on, for example, a process bus in a millisecond. So it's a very, very fast acting system. So I won't spend too much time on this, but as you can see, the interrogator is a standard 3U rack mount system, generally sits in the protection and control rack, takes a standard DC voltage supply, and is compliant with the usual modern interoperability standards defined by 61850, for example, LE and Goose, moving to 6186999. It's based on Gigabit Ethernet. We use PRP for redundancy, and we use 1588 PTP or pulse per second for time sync. Standard is that we sample at 4 kilohertz or 14.4 kilohertz, depending on whether it's a protection or metering application. But for extended applications, we can spec this up to a maximum sample rate per sensor of 35 kilohertz, giving us a bandwidth of 17 kilohertz per sensor, which is excellent for example, power quality applications. The connection to the sensing fiber is dead easy. It's a single simplex SC APC plug connector. And from that one fiber, again, we can measure up to 50 sensing points spread over a distance of up to 100 kilometers. Now we have a range of sensors, and just to give you an example of what those are like. So our current sensor, we call our photonic current sensor, or PCT. We can measure protection or metering class systems separately. At the moment, we can't do protection and metering in one current sensing device, unlike what we can do for voltage. But the key thing here is that this is a very robust sensor. It's fiber in, fiber out. It can deal with operating environmental temperature ranges from -40 to +80 as standard. And this is because, as part of the technology, the sensor knows its own operating temperature all the time, and it self-calibrates for that. So we don't have to resort to any passive temperature compensation. It actually measures its own temperature constantly and adapts to that, which means that we can cope with huge temperature swings over the year, for example, in Norway and the Middle East, where you get huge swings. And we can deploy on secondary or primary systems, and we can deploy solid core or split core, depending on the environment, whatever makes the installation easiest. For voltage, we have also launched the first commercial optical voltage sensor that's really optical and is not performing some ADC at that point of measurement. Again, we have a huge dynamic range and also temperature range. Each of our optical voltage sensors is inherently dual metering and protection class. And so we can deploy that over virtually any voltage level, from low voltage all the way up to the highest transmission level. And we partner with Condis in Switzerland, who are manufacturing experts of high voltage devices, in order to go up to those highest voltage ranges. And then just to give you an idea of what our mechanical sensors look like, we have the temperature sensors on the left and the strain sensors on the right. And those can be attached in any number of ways, like spot welding, epoxying, and even screwing them onto surfaces. And that allows us to then pick up the temperature of that surface, or the strain of it and the vibration. Now, one point I want to make, which is important, is the strain measurement. So we can measure what's known as absolute strain, which means that we don't just see the change in strain. We can monitor very slowly changing expansion and contraction of materials, which is really interesting for example, overhead line sag, because at any point in time we can tell you exactly the expansion of that line due to heat or any other issue, which is very difficult to do with most other technologies. So I've talked a lot there about how the sensing technology actually works. So we've got to the point now where we have a whole load of high quality, wide area data all brought back to one central location. And the question is, what can we do with that? Now, the first thing we can do with that, obviously, is we can publish it all on the process bus. So for example, if you have relays in there, we are entirely compatible with the relays produced by the major OEMs. So if you just want to use this system as a super merging unit and get data into your systems cost effectively, for example, over wide areas for wide area protection, or for example, for centralized protection around a substation, we can provide that data and it's entirely compliant with the standards. However, Synaptec goes further because we have access to this data. We have designed our own systems to make best use of it. So fundamentally, you've got data at rates of up to 35 kilohertz per sensor. It's all correlated and it's all available in one location. We log all that data as standard, and we have an analytics platform, some of which runs on the device, on the edge for timing reasons, and some of which runs either on your own site in your own secure cloud or on our secure cloud, depending on your IT policies. So there's a number of different things we can do with that, and we tend to think of them as broken into different timescales of use. So the fastest use of that data would be for the immediate time-critical protection and control functions. For example, replacing what a relay would traditionally do, calculating fault location, delivering effectively multi-zone fault response over wide areas. And we've got systems out there that are doing this today. But then using that same data, you can derive things on the timescale of, say, minutes to hours. So in that case, we're talking about synchrophasers, subsynchronous oscillation, dynamic rating of lines, overheating alarms on cable terminators, characterization of faults when they happen with, for example, correlation with what's going on mechanically on that system to try to determine why the fault occurred, what type of fault is it, so that you can respond more precisely. And visualizing data so that rather than it just being pure publishing on process bus machine-to-machine operations, humans can start getting involved and seeing how their system is performing live. And then finally, you've got the time scale of days and months and years, where you have now, you're building up an historical data bank of time-correlated mechanical and electrical insights on your system. And this is particularly interesting because when you're able to get wide area, very granular insights on the system, you can see changes in the behavior of groups of assets compared to individuals in that. And with that, you've got a very accurate way of determining outliers and scheduling predictive maintenance rather than being reactive. So I won't get into too much detail today on the different applications within that, but for example, in protection, there's some great applications. For example, in offshore here in the top right, you can see that with this system, we're able to instrument entire arrays of offshore turbines at a granular per turbine level. And with one system, we're able to do fault detection on individual intra-array cables. We can trip breakers along there if they are in the system or if they're built in for this. At each cable terminator, we've got the temperature live, we've got the power quality on every turbine live, and we've got the synchrophasers at every turbine. All of that from a single system rather than having 3 or 4 different systems which require a supervisor to intervene and correlate. And likewise, you've got similar centralized protection and asset management schemes in substations for on or offshore. Real-time monitoring We have dashboards that gather in synchrophasors, look at the power quality, visualize that, and show alarms when we have outliers. And for asset management, we're able to look right in at the correlation between electrical and mechanical over huge time periods. We're able to look far beyond the detail that you can get from synchrophasors right into continuous point on wave, looking at transients, looking at harmonic analysis. So I've got a couple of videos here to take us to a close on what our dashboard can do with this data. So we have our own proprietary dashboard. Although this data is made available in the process bus, you can use your own dashboard, and it can go parallelly to the existing protection and control systems you have. Our dashboard allows you to look at, per measurement location, a combination of the power quality, the synchrophasors, the mechanical aspects like temperature and strain of that asset. And we can deploy custom algorithms on there, for example, for custom notifications, alarms, correlations that you want to look at. We can see everything geographically, and we can zoom right in to the per sample level. And we can zoom back in time as well to the per sample level and see what happened, for example, in the vibration signature when you had a particular transient on the electrical side. And we built the system to be very scalable, so a single dashboard can deal with multiple interrogators. So you're not limited to 50 sensors here. You could have multiple interrogators bringing in hundreds of sensors to a central point and move between them all here. So this is quite a revolution in terms of having a lot of data quality at your fingertips for an operator. In terms of how we deploy that, we have a couple of different options. So I talked earlier about the architecture being a single interrogator per 50 sensors. So if you have multiple interrogators, we perform some of our processing, for example, the real-time protection and control, right on those interrogators. We have very high-speed, reliable FPGAs that do that in a very timely manner and can feed back control signals down the sensing fiber. We have a secure connection then either to our own cloud-based systems, which are highly secure, or local cloud-based systems, if that is your IT policy. We can deploy on that as well. And on that, we have the dashboard, we have the data logging, and we have the longer timescale analytics being run over the course of minutes and hours on things like real-time thermal rating and synchrophasors. And just to round off, you can find a lot more information about the applications of this on our website. So I'd encourage you to go there and have a look at these. But just to highlight a few of them that people are asking for today, and that we can do either far more cost effectively than all the other systems in the market, or we can enable something that really wasn't possible before. So we can do cable fault detection on hybrid and mixed lines, including those that are very long distance and including those that have multiple dips. That is no problem to use this technology for that. We can derive distributed power quality and synchrophasors on different assets that are scattered over the network or are distributed, for example, with distributed generation, so that you can zoom in and see particularly which asset is causing you poor power quality and what you should do about it. We can look at the overhead line sag in real time correlated with temperature. And we can do that without having any ongoing maintenance at those measurement locations because we have no batteries, no energy scavenging. We can do wide area current differential protection, which in a way makes distance protection a bit of a legacy technology, because if you can do differential protection over multiple sections over long distances, then that is the most reliable form of protection that you should deploy. So if you can do that cost effectively, that's a very powerful technique. And then, of course, in a local area, we can do centralized substation instrumentation and protection. So I hope that's given you a good overview. I know that I've talked fairly quickly about a lot of technical details there, and I'm sure I've raised a lot of questions in your mind, so I look forward to answering some of them. But to summarize then, we're taking to market a number of solutions based on what is a very affordably scalable and distributed and secure method for monitoring power networks and the assets and DERs connected to it. This greatly simplifies the scaling up of instrumentation on grids and substations, because it eliminates the traditional requirement for a lot of supporting infrastructure. And with that, of course, there is cost cutting. So it allows us to reach more locations to get a very granular picture of what's happening around detailed assets, or in remote assets, or over wide areas entirely, or offshore. We deploy with traditional types of primary connections. So in terms of installation procedures, it is bog standard. It is the type of installation procedures that your technicians know how to do already, with installing CTs and VTs and a couple of fiber splices. So there's nothing new to be learned there. And yeah, so this is just a perfect platform for doing any form of multi-point wide area monitoring on power networks. So, as I said, I would encourage you to go to our website, and from there you can get more information on these individual applications. You can get a bit more information on the technology as well, and the different modules that form part of our solutions. And you can also download case studies from our work with some operators in these areas, and some brochures on the technology as well. So that's at synapt.ec. So I'll maybe pass back to Saul, and we can get into some of the questions which you have inevitably asked.
Thank you, Philip. That's great. Yes, actually, we've been flooded with questions here, and Neil is scrambling to keep up. So thank you, everyone, for being patient with us, waiting for responses to some of the more detailed ones. Philip, I'm going to throw you under the bus at the beginning here. I don't know if you've got the backup in this slide deck, but some people were asking for some pictures of the sensors again, so they could understand, you know, what we're looking at. So what's this idea of a standard CT, and what does it look like, and how are we doing this secondary connection to a standard CT? It'd be maybe useful if you could go back over that.
This perhaps is a useful slide on that. So the three photographs here, and this is from one of the early offshore installations. In the middle installation, you can see the phase cables from the offshore turbine coming up through the floor and being split into individual phases. Now what we're doing there is we have 3 split core CTs, and you'll see that they just look like traditional split core CTs, because they are. But the secondary of those CTs is going to a local box, which is converting those immediately and passively into optical signals. So where we're able to, we like to install around insulated cables like this, because it reduces, of course, the requirement for us to come along with costly insulators to protect the device. It means that we can install, because we don't have any copper secondaries, it means that we can install while the system is live. But in other situations, of course, we use traditional standoff insulators, for example, in outdoor installations. Let's see if I've got any photographs of that. I don't have any photographs of that today, so.
No, that's okay. I think that helps, because the question was just to see some installed. We should point out that a lot of the examples we're sharing here, of course, are HV applications, and I think the question was actually about distribution. So we should point out that we designed and built these systems to make sure that we were good enough for transmission grade protection and control applications. But what we have not yet installed a system at medium voltage within a distribution network environment, but of course the operating principles for protection and for monitoring are the same.
Although I would point out that we do have a system live at the Power Networks Demonstration Centre, which is a Scottish outdoor MV demonstration centre, and there we have overhead line voltage and current sensors installed. Okay, and then one of the other common questions, Philip, if you could just go back over this for everyone. So there were some questions about just recapping on the voltage levels that this is appropriate for. And you mentioned a little bit about retrofitting, you know, working secondary of the output of some of these things. Could you just go back over the voltage levels for people? The voltage levels on current or voltage sensors, or both? Well, for completeness, you should do both, because it was voltage levels, but you may as well address both points. Okay. For measurement of current, voltage level really comes down to insulation, as I'm sure most of you know. So for example, here in this picture, we're measuring current, but the voltage is insulated, so we're not concerned about that. In terms of insulation, for example, with higher voltage levels, in our facilities in Glasgow, we build sensors that are qualified up to 100 kV installation, in which case you have a traditional looking standoff insulator that has a dielectric fibre running through the centre of it to take that over to the primary side. That fibre is then connected to our current sensor, which is situated at the top of the standoff insulator. And to go up to 600 kV, we work with our partners in Switzerland, who qualify up to 600 kV. But the approach and the technique is very similar. Likewise, on the current side, we can go from low currents all the way up to the highest primary currents, and we can cover, you know, the protection classes like 5P40, where we have to have a significant dynamic range. Does that answer the question, Saul? Do you want me to go into any particular detail about that?
It wasn't more specified than that. I also noticed that just a general question here for the everyone who's attending here. A couple of people have put their hand up during the presentation, so presumably you had some questions in mind. If you could just type the questions in the Q&A session, we'll be able to capture those questions there. So I can see two of you had your hand up here, and I wanted to be able to respond to you, but it would be good to keep it all on the Q&A so that we can track it and follow it and make sure we've covered all the questions for you. Now, I've got two more that are really in-depth ones for you, Philip, so that have come up. So have fun with this. The first one that I thought was interesting to explore was you mentioned continuous point-on-wave measurement and synchrophase in passing there. Yeah. So one of the questions that came up was, well, hang on, can you explain how you compare what we do with existing PMU systems that you'd see in like HV substations? Yeah, that's a good question. So PMUs, phasor measurement units, and synchrophasors, what they give you is a time-stamped phasor measurement, which is going to be an amplitude and a phase at a particular point in time. So the way the standard defines that is you've got a point in time, and from the last cycle, say, you've calculated your phasor. So you've got a sinusoidal wave, and you give, here's the amplitude and the phase of that. But you've actually thrown away quite a lot of information in doing that. You've given away information on the harmonics. You might have captured a few of them, a few discrete harmonics, depending on the standard that you're working to, but you've thrown away the rest, certainly the majority of information, certainly transients. So continuous point-on-wave sets out to address that. So there's been work done by NASP in America, by National Grid and others in the UK, to see how we could move to a system from synchrophasor-based systems to continuous point-on-wave, in which case you're not calculating the phasor and transmitting that, you're literally transmitting all of the measurement data sample by sample back to a central location, which sounds like a gigantic IT challenge, and it is, because there's a lot of challenges there in terms of bandwidth and data security, but that's where we're able to help. So because our sensor networks are all passive, we don't need that infrastructure to be there. Because we timestamp everything at a central location, it means you don't need to distribute network time over to each of those measurement locations, nor do you need to have the alternative, which is GPS access at each of those locations to get a good timestamp. Okay, so we have patents around that. How we capture the time in a central location and shift everything. So at a central location, we can gather in, say, 50 measurements, all of the voltage at different points in a system, and we've got every single measurement sample time correlated. So from that, then we can go into, as you can see here, the real detail on the system and look at oscillations, transients, and more importantly, the correlation in a sample by sample between what's happening in different points in that system, which is information that you can't get from synchrophasor data, because for reasons of data efficiency, it is thrown away traditionally. But there's a huge amount of insights and value there if you can capture it. The question is, can you capture it cost effectively? And that's exactly what we're setting out to do. I think that covers it. Maybe, Philip, one other thing to mention is where you touched on synchrophasers. I suppose it might be worth explaining that, you know, if you've got this ability to deploy lots of sensors over a wide area, then of course, if we're using light through fiber to bring those signals back, you've got a more efficient way of collecting lots of synchrophasers over a wide area without needing very complicated IT infrastructure or communications infrastructure and layers of phaser data concentrators and so on, right? And there's a networking benefit as well there, correct?
Yeah, that's exactly right. The traditional way of doing this is you have multiple powered PMUs, and then they are all measuring independently, and they are feeding their time synchronized phasers back to concentrator units, who are then feeding it up a chain again. And this requires dedicated telecom systems that are really well spec'd in terms of distribution of time and the latency by which they can get packets of that data back to a central location for use in a time frame that makes it still valid for use. So we simplify that a lot.
That makes sense, thank you. And then a couple of questions have come up about how our technology will apply to monitoring cables. Now, so some people are talking subsea, some people are talking underground, of course. So it might be good if you could talk about anticipation or prediction of failure, because we were talking about power quality in one section and the fact that, you know, you could see certain harmonics which might be harmful according to the academic literature we know about to sort of like the premature aging of cables. But in terms of our ability to monitor particular locations, terminations come to mind for me. How does that, to what extent can we predict cable failures and sort of look ahead rather than the protection response to a fault once it has occurred?
Yeah, so that's a very good question. So obviously we can respond to the fault when it has occurred, and we can do that more granularly than a traditional protection system. That's nice, but the real question is how much in advance can we predict that that fault's going to happen so that operators can intervene before it becomes a problem. So this is something that we think about a lot at Synaptec, both for offshore and underground cable applications. Now, there are, if you can get data on, for example, the terminator, cable terminator or junction box temperatures and the power quality at all the infeeds correlated with the current, then you can start to get a full picture of the reasons for degradation and the sources that are causing, for example, low power quality. As you said, Saul, there is a correlation for sure between low power quality and long-term damage to cables, because harmonics both hide energy that's being dissipated, usually by heat, in that system, and also particular harmonics are known to cause particular issues. And it's often not feasible to eliminate these issues prior to building a network of, for example, distributed generation. It's only once it's been built these networks these problems can come to the fore. So we deploy systems that can measure the temperature, the current, the power quality, and also deal with the faults and fault location for underground and subsea and offshore systems. And our approach is ideal for that, because often in these ducts you have fiber, but you don't necessarily have a low voltage auxiliary power supply, nor do you have the capability to use wireless sensing because it's underground, so the signal can't get through, nor can you put up with the variability of the signal from wireless sensing. So you've got to think, what can I get high quality real-time data back to a central location for? Well, I've got the fiber there, so this is an ideal way to deploy sensors, to deploy those groups of sensors and get them back and correlate that information. Then from looking at the temperature, you can start to correlate the current with the temperature for every one of the terminators. You can establish what's a kind of cloud of normality for that, and you can start to correlate that with the variations in power quality. And then you can start to identify which assets may be causing poor power quality and get a feel for which cable sections are likely to begin undergoing degradation of their lifetime.
Okay, thank you. Now, we've probably got time for one or two more questions. I'm conscious that we shouldn't take up too much of people's time, as we've come up to 45 minutes already. So just scanning through the Q&A, I think Neil's been very busy there answering most of them, and I think I've recounted the most popular ones. I'm just checking. One thing maybe to explain upon again, so some people were asking about the output from the interrogator. So on one hand, we've said, yes, we're streaming 61850 sample values, so 9-2. Can you talk about two things then? So what are the other data formats, and outputs we could support if people want data in certain different ways, and maybe sample values aren't the only way? And then also for 61850 can you talk about interoperability a little bit, please, and how we're sort of compatible with other manufacturers' devices supporting that standard?
Okay. So as standard, we output in 61850 because it's the COM standard that people are moving to and adopting. But at Synaptec, we have a team of engineers that span the hardware all the way through to the software, and we build our own stack for 61850, for example. And if there are requirements out there for other standards, like Modbus, for example, we can implement that. That's not a problem. We can support it. We can also output synchrophasor data directly, for example, in the C37118 standard or the IEEE equivalent. So the answer to that is that we, as standard, do 61850 and 61869, but we're perfectly capable of doing any standard output format as required. In terms of interoperability, we think of that in terms of 61850, and we've shown interoperability with devices manufactured by ABB, GE, Schweitzer, and so on. And we've shown that, for protection applications, that taking the whole scheme as one and doing an acceptance test of the whole scheme from tripping signals through the relay down to the super merging unit, down to the individual sensors operating over wide areas, the whole thing is completely compliant with the protection standards for accuracy, for trip times, and so on. So the scheme works well, and it plays nicely with all the other major manufacturers' devices, which is great because some operators want to stick with their existing relays, which is fine. There's a lot of functions on existing relays, and others want to focus in on particular functions that would be implemented on our device so that you don't need a separate relay. But either way, we're very flexible.
Okay, great. And then thank you for that. There are a few questions still flying around about this. I'm going to make you repeat one thing again there, Philip. So sorry to do this, but there's still some people out there asking questions, saying they're still slightly confused about how we're connecting those sensors. So the splicing back into fiber and, so again, we probably need to clarify, if you would, between how we would primary connect or secondary connect, and then how we bring the signal from that sensor point back, just so it's clear, because it can get confusing when you think about secondary connection or retrofitting as opposed to primary.
Okay. Let's go back to the technical sheets on the sensors, just so that I can describe the inputs and outputs from them and connections. So let's take this as an example. Here we have a medium voltage sensor measuring up to 70 kV. The top of that is going to be live, and the lower part is going to be earth. And we're going to be measuring the potential between those two. The sensor is embedded inside it. The fiber is the only connection to the external systems. We have a fiber in and one fiber out, dielectric, single mode, no copper in and out whatsoever. So that will make a primary measurement of voltage, for example. If we wanted to make a secondary measurement of voltage, it would be the same technique, but it would be a device spec'd for attachment to the secondary side, for example, of an existing VT that was in situ. Likewise, for current measurement, again, it's one fiber in, one fiber out that leads to the next sensor, because all the sensors can be connected together in series. And on the electrical side, we have the CT for around the primary current, or if we want to measure the secondary current, we can provide modules that connect directly to the secondary of existing CTs, or are installed in the bay cabinets in a substation, for example, that read the secondary currents from existing CTs, but they operate passively and they take the secondary current and convert it into our optical signal. So for all of our sensors, there is always a conversion from the electrical domain to the optical domain. There is always only a single fiber connection and an optional fiber output to take it to the next sensor, because you can daisy chain them. And the connection of the primary or secondary connected devices is exactly the same as would be with traditional CTs and VTs or traditional merging units, except that you do not need to have any power or time sync on those devices.
Okay, and a supplementary question on that one, which I think I was answering correctly by typing just a minute ago, but you better keep me honest because I'm not the expert. When it comes to the sort of VTs where we would build them and put our sensor head inside of them, I believe they're not all oil filled, are they? I can't remember exactly how they're constructed.
They're not oil filled
in terms of what.
No, we avoid oil.
Okay, and speaking of VTs, there was a question asked, which is probably appropriate to answer here about, you mentioned Condis and their feature on this slide here. So could you just explain to people what the interaction with Condis is in terms of, how we're using it for the equipment and to build up the final products you're seeing?
Yeah, so Condis are a close partner of ours, and they are experts in high voltage engineering, whereas we are experts in instrumentation and analysis. And so together what we do is we deliver the systems that are above 100 kV. So if we're doing primary measurement above 100 kV, it's a partnership between Condis and Synaptec that delivers that.
Yeah, I suppose it might be worth sort of repeating again that the idea here is that the CT or the VT that you would see in the field looks like a traditional one. It's just that we've only got a fiber connection instead of a power connection to them. So it's a very familiar form factor in terms of how you'd install it or what techniques you would use to deploy them or retrofit them anywhere. Would that be a fair summary?
Yeah, that's right. So.
Okay. All right. Now, I am probably going to suggest that looking at the time and looking at the number of questions I think we've answered so far, it would be fair to give everyone a break now as we get close to 3 o'clock in the UK, because people always have, meetings at the top of the hour to move on to. I can see some people asking it's time to leave. I can see there's a few more supplementary questions being asked here. So we're going to keep this conversation in terms of the Q&A panel open for a couple of minutes at the end of this call now, in case there are any final questions that we needed to answer. But of course, if it's going to be more in depth and we've just teased you and you've provoked more thinking and questions, then we invite you please to get in touch with us at hello@Synaptec, or of course, you can get through to us from the website. We're on LinkedIn as well. So there's a scope to ask more questions and get more in-depth answers. I know some of you have got very particular questions, for example, about the maritime sector and autonomous shipping, which I think we're going to have to answer separately because it's such a specific application requirement. So we've noted that one, and we'll get back to you individually on some of those very niche application questions. But for now, can I just say thank you to Philip for taking everyone through all of this stuff. The presentation is much appreciated. We are obviously recording this so that we can keep a copy of it and put it up online later on. Any outstanding inquiries, as I say, we'll keep a track of those Q&As, and we'll be back in touch with everyone who kindly was able to participate, and make sure that we've answered any outstanding questions. Do keep an eye out for more webinars coming up from us in the near future, because we've got a series of these running the rest of the year, as I said before, covering other specific applications. So we'll go more in depth on centralized bus bar protection or overhead line monitoring, and I hope that's of use to all of you. So do keep in touch with us, and we'll try to keep you up to date with how our business is growing in these applications, and how we add value to the operation of these networks is evolving. So for now, thank you very much, and we'll conclude the audio part of the webinar now, and then we'll be finishing off answering some questions on the Q&A panel online after.
Just like to add, thanks very much for listening, and I hope it made sense. But if anything didn't make sense and you want some more information, please don't hesitate to get in touch, because we love getting into the technical detail on this and finding out the other applications that people have for the technology beyond the ones that we've envisaged. And as Saul said, you know, I flew through quite a lot of applications today, but the other webinars that are coming up will go into more depth on those particular individual applications. So if that's what you're looking for, please look out for the new webinars. So thanks very much.
Yes, thank you everyone. Goodbye and have a good day.